What's up, guys? Welcome to Calculus Club. In this video, we will be talking about continuity and discontinuity. All right, let's get into it. So, first off, a continuous function is exactly what you think it would be. If there are no holes, nor no gaps, no vertical asymptotes, then we say the function is continuous, okay? You can see here that this would be a continuous function. And of course, if there is a hole, we say that it is discontinuous. So there are essentially four types of discontinuity, all right? So the first type is a point of discontinuity, and that's what you just saw. That's just where you have a hole in the function. So just a single point is discontinuous. The rest of the function would be continuous, okay? You also might have an infinite discontinuity, which is essentially a vertical asymptote, okay? So if you have a function, if you have like a vertical asymptote here, then you have a infinite discontinuity, okay, at that vertical asymptote. The next one is a jump discontinuity, which usually occurs when you have a piecewise. So it might be something like this. Okay, you have this jump discontinuity here. And the last type is a really kind of special one that doesn't occur very often, but I want to mention it. Okay, and this is an oscillating function. So like y equals sine of 1 over x. What's going to happen is this is going to oscillate from -1 to 1, and then as you get closer to 0, it actually oscillates faster and faster and faster. So it continues to go up and down, up and down, up and down, increasingly fast at 0. And I can show you this here using Desmos. So here is the function, sine of 1 over x, and notice when I zoom in, this function is just going up and down and up and down increasingly fast, okay? And that would do that forever, never actually getting to 0. At 0, it would be discontinuous because you're dividing by 0. All right, so those are the four types of discontinuity. Now, let's think about the function f of x. What actually occurs on f of x to make it discontinuous? All right, and the most common situation is simply when we divide by 0, okay? So when you have a 0 in the denominator, this could be 5 over 0 or 0 over 0, all right? Now, I skipped this part. Keep in mind that 99% of the time, a function is continuous, okay? It's only in a couple special circumstances where a function would not be continuous, and I'm going to mention these now, all right? So the most common one is when we divide by 0. If ever you divide by 0, then the function is discontinuous, okay? Now, when you divide by 0, if you divide by 0 and you get a number over 0, okay, that will always be a vertical asymptote. And I've already talked about that. That will be true 100% of the time, okay? Number over 0, always vertical asymptote. Now, if you get 0 over 0, all right, that will vary. Actually, sometimes 0 over 0 will be a point of discontinuity, okay? Sometimes 0 over 0 will be an infinite discontinuity. Sometimes 0 over 0 will be a jump discontinuity, okay? If you get 0 over 0, you need to do a bit more work to determine the type of discontinuity, okay? Most often, it will be a point of discontinuity, okay? In most situations, it's a point. But there are a couple special circumstances where you might have the infinite or the jump discontinuity, okay? And to determine, right, you won't do this too much, but if you really want to get in a lot of mathematical depth to determining the discontinuity, what you would do is take a look at the limit from the right, from the left, and from the left or right, I don't know what you're seeing, right? And figure out if those two, don't equal one another, then that's a jump discontinuity. If the two equal one another, it's a point of discontinuity. And if these shoot off to infinity, one of them does, you have an infinite discontinuity, okay? But you don't really need to do that too much. That's just how you would do that without a calculator if you wanted to do it in a very mathematical way by hand. All right, so anyway, that's the first situation, a 0 in the denominator. The next situation is where you have a piecewise discontinuity, okay? So, for example, here, x plus 2, x squared plus 1. So if I were to draw these, x plus 2, x squared plus 1, you can see that you have a jump discontinuity there, okay? And these are actually the two situations where you might have discontinuity in the middle of the function. That's when you divide by 0, or when you have some piecewise discontinuity. The next three situations I'm going to mention here are more something like a domain. There are some x values you would not include in the domain, right? The first one would be like if you have the square root of a negative. So for example, if I graph the square root of x, you don't include any negative values. So the function goes until 0, but then it becomes discontinuous to the left of 0. And that's simply because those values are not a part of the domain. This will also be true for the next ones if you have a log or a natural log. All right. If you remember what these look like, okay, log x, your domain is from 0 to infinity. So again, anything less than 0 and 0 also does not exist, okay? The natural log, so the log x has a base of 10, all right? The natural log has a base of e, and again, only continuous from 0, not including 0, but from 0 to infinity. And then log base 5 of x here, same thing, 0 to infinity, not including the 0, okay? So those are all the situations. Oh, one more. The last situation is simply when you have a domain restriction, right? That is telling you x greater than or equal to 0. Sorry, my eye itches a bit. Yeah, so those are the main situations where you would have a function that is discontinuous. So now what I want you to do is I want you to pause the video and I want you to think about all 5 of these functions. Are they discontinuous or are they always continuous? If they are discontinuous, then tell me the type of discontinuity. All right, so I hope you paused the video. I hope you worked through all of these and you thought about them, okay? So for the first one, 1 over x, well, when x equals 0, the denominator is 0, so we have discontinuity at x equals 0, and at x equals 0, you have 1 over 0, which is a number over 0, which means you have a vertical asymptote, or an infinite discontinuity. So the function looks like this. You see that it's continuous everywhere except at x equals 0, okay? The next one, again, we know that it is discontinuous at x equal 1 because, again, a 0 in the denominator. Now, for this one, you should have already seen when we evaluate limits analytically. What you can do with this one is you can factor. So you can rewrite this one as x plus 1, x minus 1 on the top, x minus 1 on the bottom. And these x minus 1s cross out. And whenever you're able to cross out that discontinuity, then you know it's going to be a point of discontinuity, okay? So you have a point of discontinuity at x equal 1. Point of discontinuity is also called a removable discontinuity, which I'll talk about in a second. But yeah, this is what the function looks like. You have a point of discontinuity. All right, so on this one, we need to think about what's happening to the left, what's happening to the right. Well, as we approach 0 from the left, we are going to be approaching 0 plus 1, which is 1. And as we're approaching x squared plus 1 from the right, we're going to get 0 squared plus 1, which is also 1. So since these two approach the same value, this function is actually continuous, okay? You can see at 0 that these meet, the left and right limits meet one another at the 0. Okay? Of course, if any of these were shift up, if this was like an x squared plus 2, right, this would shift up here, and there would be a hole there would be a hole here, right? And this would be discontinuous, but as it was written, it was continuous. All right, so this is kind of a special case, the absolute value of x over x. And this one, again, at x equals 0, the denominator is 0, which means it's going to be discontinuous at x equals 0. And this one is a very special one. It's one of the only cases where you actually have a jump discontinuity, but you do not have a piecewise. Okay, so here you have two holes here. They don't exist at either of these, but you have a jump discontinuity on this function. Okay, and the last one, this function here, you actually are going to have two places of discontinuity, two places where that denominator is 0, and that's at x equals to 2 and x equals to -2. All right. Now, if I plug in, well, let's factor this. Okay, so the first thing I'm going to try to do is I'm going to factor these to see if anything crosses out. And I get x plus 4, x minus 2, over x plus 2, x minus 2, okay? So the x minus 2 crosses out, which means this x equals to 2 will be a, I don't know why I wrote POI, sorry, that's point of inflection, that's something totally different. X equal 2 will be a point of discontinuity. Okay, also called a removable discontinuity. So a point of discontinuity at the x equal 2 because I remove it. All right. Now at -2, what you're going to notice is this is actually, if I plug in everything here, that's going to be a -4 over -4, which is just 1. -2, when I plug in there, is going to give me a +2 up top and a 0. So I would get, let me just put it 2, 0, and then these would be a -4, -4, right? Which is just a -8 over 0. Number over 0, what does that mean? That means a vertical asymptote, okay? So that's always going to be a vertical asymptote, all right? Sorry, adjusting the color a little bit here. Yeah, so that's always going to be a vertical asymptote. So when I graph it, the function is going to look like this. We have our vertical asymptote at -2, okay? And then we have a point of discontinuity at the +2. All right, almost done. And I'm running out of light here because the sun is setting. That's why I had to focus a little bit, change the lighting, okay? So I've already talked about it, removable versus non-removable discontinuity. Okay, so a removable discontinuity is a point of discontinuity. And the reason it's called removable is because we can redefine the function to make it continuous. Like you can simply plug in, you can fill in this hole by just redefining the function. So if we allow the function to be the x squared plus 2x minus 3 over x minus 1 for all values except for 1. And then at 1, we allow it to be 4. We have essentially redefined this function and made it continuous. Okay, so we have essentially removed the discontinuity. All right. You could also just rewrite this as x plus 3, right? This would like factor x plus 3, x minus 1 over x minus 1. Right? These would cross out and you'd simply get x plus 3. That's the exact same function except the hole is now filled. All right? All other discontinuities are non-removable. All right? And it's pretty easy to think about why that is. So if I have, for example, this infinite discontinuity, I cannot make this continuous in any way. Right? There's nothing I can do to make that continuous. Also, if you remember back to the definition of functions, right? And if you remember back to the definition of functions, you cannot have, for one input, one x, you can only have one y, right? There's a thing called the vertical line test. So we cannot create a function with more than one y values for one x. All right, vertical, clearly we can't. Jump discontinuity is even better because it's not, it's not such a huge line. Like we cannot just redefine this function and make this line to connect these and make this continuous because then this is no longer a function. So that is why we cannot remove the discontinuity, okay? So the most important thing is just remember a point of discontinuity is a removable discontinuity. There's a very good chance that this will come up in your class, and all other situations are non-removable discontinuity. Okay, so the last thing I want to talk about is the mathematical definition of continuity. Okay, so a function is continuous at x equals c if the following are true. All right, the first thing that must be true is that f of c needs to be defined. So x equals c must exist. X equals c must exist, okay? That is the first necessary condition of continuity, okay? The second condition is that the limit as x approaches c f of x must exist, all right? So now what I want you to do, okay, in order to try to figure out the third condition, which is really like the main binding condition of this, see if you can draw a function where 1 and 2 are true, but the function is not continuous. Okay, pause the video and try that for a second. This is an interesting thing to think about. All right, so I hope you paused the video and you tried this, all right? So if I have, for example, so I'll show you the condition. Like, let's say that this is my function. Let's say that this is c here. Well, here is the situation where f of c is defined, right? It equals to whatever. Let's say that that's L. So f of c equals L, okay? So 1 is true. The limit as x approaches c, f of x exists because both the left and right are heading to the same point, okay? So the limit exists, but the function is not continuous. You have a point of discontinuity, okay? So how could you make this continuous? Well, you could make this continuous if you move this point down and put it in this, put it in the hole, right? So what could be the third condition to make all this true? Well, that f of c equals to the limit. So the main thing about mathematical definition of the continuity is that the limit as x approaches c of f of x equals to f of c. So that's the big thing to remember, okay? And that's the mathematical definition of continuity. All right, so that is all for this video. Thanks for watching. If it was helpful, if you could give me a like, comment, share with your friends. That really helps me to reach more students. So thanks for watching, and I hope you tune in for the next one. Bye-bye.